semester. So welcome to this. Okay, welcome everybody to this lecture on quantum field theory, relativistic quantum field theory. I hope you had a nice vacation time and are ready to begin once again with physics. Most of you are probably now starting your master's degree in physics, and this is maybe one of the first or even the first lecture that you attend in the new semester. So welcome to this. And this lecture is, as the title says, on relativistic quantum field theory. It's an introduction into this topic. Quantum field theory is quite a vast topic actually, and so one semester on quantum field theory will not be sufficient to cover all of the interesting material on quantum field theory. And therefore actually I wanted to call this lecture Quantum Field Theory 1b, for a reason that I will explain later on in more detail. So my name is Dominik Stöckinger, of course. We are clear on this. And this lecture is part of our specialization area, and in fact you can use this quantum field theory lecture for two different specialization areas. You can use it either for particle physics specialization or for theoretical physics specialization. And as you see, the lecture is videotaped, and so we want to put the whole lecture series on YouTube. And maybe you know that in the past 3 years ago, 2019, I also recorded a Quantum Field Theory 1 lecture series, and it's also completely on YouTube, and that would be Quantum Field Theory 1a. And so that lecture from 2019 is also an introductory lecture on quantum field theory, but it will be different from this one, but both of them will be, let's say, suitable for a first encounter with quantum field theory, and they will take you from quantum mechanics knowledge to a knowledge and understanding of quantum field theory. So let us begin with some thoughts on relativistic particles. So let us imagine you have here a particle, maybe a point particle like the electron or the proton or some other particle which is small. Then according to quantum mechanics 1, you know that you can localize this particle, and you might want to localize it better and better. So you confine the particle into some measurement device maybe, or simply some device which forces the particle to be in a very, very well localized position with an uncertainty of only delta x. Then you make the localization better and better, so delta x becomes smaller and smaller. Delta x ultimately should go to 0 such that the particle is perfectly well localized. Then the question is whether something special happens. And according to your quantum mechanics knowledge, of course, you know that something happens, namely there is a momentum uncertainty, and because of the quantum mechanical uncertainty relationship, delta x times delta p must be bigger than h bar over 2. So if delta x becomes small, delta p automatically becomes big, and ultimately it should go to infinity, or it becomes bigger than any number that you prescribe. Okay.
طبعا هنا في نقطة معينة، دلتا اكس تعتبر في درجة مكانية، دلتا بي عبارة عن 1 على دلتا اكس، تعتبر معدل تدفق المكان. هذا من ناحية كمية، من ناحية كوانتمية. من ناحية فيزياء كلاسيكية، دلتا بي يساوي التغير في السرعة m مضروبة في دلتا في. دلتا في عبارة عن ماذا؟ معدل تدفق بالنسبة لمعدل تدفق الزمن، يعني معدل تدفق المسافة بالنسبة لمعدل تدفق الزمن. لكن معدل تدفق المسافة بالنسبة لمعدل تدفق الزمن لا يصل إلى كمية إلى لا نهاية. صح، هو كلما زاد السبيسنج أو سبيسنج أو كما يقال الفضاء، مدارات الفضاء كلما زادت فهذا يعني يزيد النسبة بين معدل تدفق المكان إلى معدل تدفق الزمان، لكن لا يمكن أن يصل لما لا نهاية. لكن كوانتميا يفسر أفضل إنه الإكس هو الفترة المكانية والبي هو عبارة عن بارشل على بارشل إكس أو دي على دي إكس، ويعتبر معدل تدفق المكان، وبالتالي كلما نقصت الفترة المكانية كلما زاد معدل تدفق المكان. وربما يكون رأيت في الفيديو السابق لهذا مباشرة أن معادلة ديراك تم إثباتها وتم يعني التحقق منها عن طريق معدلات تدفق المكان والزمان. طيب نواصل.
But in a relativistic sense, the energy is related to the momentum by energy is given by square root of p square plus the rest mass of the particle square. And so therefore, if you have a momentum uncertainty in any component of the momentum, then the energy uncertainty is at least as big as the uncertainty of the momentum. And if the momentum becomes really, really big, you can forget about the rest mass, and ultimately you simply have an energy uncertainty which goes like delta p. And so the energy uncertainty also goes to infinity. So that means if you localize a particle better and better, and the particle behaves according to special relativity, ultimately you have an energy uncertainty which is bigger than any prescribed energy. And so at some point the energy uncertainty is bigger than, for example, 2 times the rest mass of the particle, and therefore you have enough energy available.
طبعا E كوانتميا عبارة عن بارشل أو دي على دي تي، وبالتالي أيضا تعبر عن معدل تدفق الزمان. وبالتالي إذا حصرت الجسيم مكانيا في مسافة ضيقة جدا فإن معدل تدفق الزمان ومعدل تدفق المكان سيكونان كبيران جدا، وهذا ما يسبب بما يسمى بالmeasurement problem.
To produce new particles of the same kind, or even particle-antiparticle pairs of that kind. And that is the decisive new feature that appears if you combine quantum mechanics with its uncertainty relation and relativity with the energy-momentum relationship. So we can create new particle-antiparticle pairs. And this shows you that something fundamental is going on when you combine relativity and quantum mechanics. And this fundamental new observation is that a single particle theory for relativistic quantum particles makes no sense. There is no such thing as a consistent single particle relativistic quantum theory. In other words, to say it in a positive way, relativity plus quantum mechanics requires multi-particle theories with the potential to create or annihilate new particles or particle-antiparticle pairs. So therefore the combination of quantum mechanics plus relativity does not result in just some slightly modified quantum theories, maybe with a modified Schrödinger equation with different derivative operator or so, but it requires fundamentally new concepts which allow the creation and annihilation of particles. So that is a fundamental observation that you can obtain in this very simple way. And this observation, of course, explains also what we have seen in quantum mechanics 2 lectures, where so some of you might have attended quantum mechanics 2 with me or with other lecturers. So there you analyze Dirac equation or a Klein-Gordon equation as a single particle quantum mechanical equation, and you discover lots of internal inconsistencies. And those inconsistencies are simply due to the fact that there is no such thing as a single particle relativistic quantum theory. Such theories can only ever be approximations, for example, for low energies. So this is the reason why single particle Dirac or Klein-Gordon equations are ultimately inconsistent. And therefore new concepts are needed. And at this point I would like to refer you to the videos from 2019. So let's say quantum field theory 2019-20. Okay, so let us then define what quantum field theory really is. Very briefly, quantum field theory in a nutshell What is quantum field theory? First of all, quantum field theory is a certain subset of all possible quantum theories. So every quantum field theory at first is a quantum theory. That means all the very, very basic quantum mechanical postulates that you know from quantum mechanics lectures are valid also in quantum field theories. That means quantum mechanical states are represented by Hilbert space vectors. Observables are represented by Hermitian operators which act on those states. Probabilities are given by squares of probability amplitudes, and probability amplitudes are obtained by taking scalar products between different states represented by those Hilbert space vectors. So all those postulates are valid in all quantum theories, in particular also in quantum field theories. But quantum field theories have now a special additional property, namely the basic observables and the basic operators which act on our Hilbert space of states have a property, namely operators, and in other words observables particular have the form that they are depending on space and time. Operators, or at least the basic operators out of which you can reconstruct all the important operators, they are local in the sense that they are defined as a function of x and t, and so they are like operator fields or field operators, and by integration or combining such operators, you can obtain all operators of relevance in a quantum field theory. So that is the essence of quantum field theories. And now you can ask, where do we need them? And the answer is everywhere. Quantum field theory is the basic language of all modern physics, and you can apply it in all modern theoretical physics contests like particle physics, nuclear physics, condensed matter physics. So let me just give a few examples. So of course we need quantum field theory to describe elementary particles and also nuclear physics. And in this case, we actually need relativistic quantum field theory. And that is then the answer to the problem that we have explained before. There is no point in localizing particles, and therefore single particle relativistic quantum theories do not exist, and the replacement of them are really relativistic quantum field theory. But also in condensed matter theory, non-relativistic quantum field theories are extremely useful, and in many other subjects as well. I only list here also cosmology, where we need actually particle physics, we need nuclear physics, and we even also need to some extent condensed matter physics to understand the behavior of the cosmos as a whole. And of course all of that is in the background of gravitation, so here we need really relativistic quantum field theory combined with general relativity. So why is that? Why do we need quantum field theory in all these contexts? And let me just explain here in particular how quantum field theory resolves the paradox from before, namely we cannot have a single particle relativistic quantum theory. Thinking about the previous discussion in particular means that one operator which you are all familiar with from quantum mechanics doesn't really make sense in a relativistic quantum setting, namely the position operator, which is one of the simplest operators of all, and you are very familiar with position operator. But the discussion shows that position eigenstates are not really possible in a relativistic theory, because before we can really localize a particle, in other words, before we can prepare experimentally a position eigenstate, we create additional particles and antiparticles in pairs. And so therefore the position operator is really dubious, at least maybe impossible to obtain, or at least we cannot have it in the same form as we are used to. And what is the replacement of the position operator? And that we can easily understand by really thinking carefully how a position measurement is actually done in experiment. Because an experimentalist measures the position in an indirect way. And you know that already from very early quantum mechanics discussions, when the position measurements were usually done by having photographic plates and so on, particles hitting photographic plates and then creating some chemical reaction in the photographic plate and so on. So what is really a position measurement? Let's draw it a little bit. So here you would have a particle, and the position measurement is done by the particle hitting a screen, and the screen is either a photographic plate, or nowadays it would be an SSD chip or some calorimeters in particle detectors, which are composed of many calorimeter cells. Each calorimeter cell or each molecule on a photographic plate is independent of all the other ones, and then the particle hits the screen, and that means it hits one of those calorimeter cells or one of the molecules in the photographic plate, and here some reaction is created, either a chemical reaction or the calorimeter cell creates an electric current, which is then registered by some electronics. And then what is done by the electronics is that this is read out afterwards. Interpreted as a position measurement, but what really happens is a chemical reaction in one of those calorimeter cells, and that means what we really measure is the energy deposition as a function of the position of the calorimeter cell. So the real measurement is energy deposition as a function of the calorimeter cell. And so we could say the observable that goes along with it is energy density as a function of position. So let's call it rho hat for an operator of x and t. That is really the observable that is measured. And so you see that in replacement of the position operator, what we really have in the actual experiment is a local observable, namely energy density, which depends on x and t, and that is measured. And so here you see that really such an space-time dependent field operator replaces our position operator. And in this sense you can understand that quantum field theory can come to the rescue of our non-existing single particle relativistic quantum theories. Similarly, let me also indicate why in condensed matter physics quantum field theory might be of interest. So in condensed matter physics you have many molecules or atoms or ions, maybe densely packed and so on, and they interact with their next neighbors or next to next neighbors, but anyway they have kind of short range interactions, and what we are often interested in is the long range physical behavior of the condensed matter system. So we are interested in phenomena which take place at distances which are much larger than the distance between one degree of freedom and the next. And so in this way we can perform the limit where the distance between neighboring molecules goes to zero while we keep our macroscopic distances fixed and large, and then we can approximate very well the condensed matter system by a continuum where we have continuous degrees of freedom which are localized at all x and t. And so therefore such a field theory is a very good approximation of condensed matter physics. And in particular it can be used to study long range or next to next neighbors, but anyway they have kind of short range interactions, and what we are often interested in is the long range physical behavior of the condensed matter system. So we are interested in phenomena which take place at distances which are much larger than the distance between one degree of freedom and the next. And so in this way we can perform the limit where the distance between neighboring molecules goes to zero while we keep our macroscopic distances fixed and large, and then we can approximate very well the condensed matter system by a continuum where we have continuous degrees of freedom which are localized at all x and t. And so therefore such a field theory is a very good approximation of condensed matter physics. And in particular it can be used to study long range phenomena. And examples are phases, phase transitions, but also excitation spectra or excitations in general of collective modes or quasi-particles. And quantum field theory is the perfect language to study all these aspects of condensed matter systems. All right, so this ends our motivation of quantum field theory, and let me now give you an overview of what we plan in this semester in the lecture. And here I will also explain the complementarity between this lecture here in this semester and the lecture from 2019 and 20. And I explain it in this two-dimensional diagram of quantum field theory aspects, because quantum field theory unifies quantum mechanics and relativity, and so there are on the one hand quantum aspects, and on the other hand there are aspects related particularly to relativity and also to particle physics and the types of particles that are described by our field theory. And so what are the quantum aspects? There are quantum aspects, for example, one can study free fields and free particles. One can study interactions and Feynman diagrams, Feynman rules. One can study renormalization at higher orders where there are divergences appearing in Feynman diagrams. One can study non-perturbative aspects and exact relationships, exact theorems in quantum field theory. One can study the renormalization group, which is a very important and modern subject, and so on. And on the other hand, one can study different types of fields and different types of particles organized by the spin, because relativity tells us that there are particles and fields of spin 0, spin 1/2, spin 1, and so on. So we can organize it according to the spin, and the list ends at spin 1. Afterwards it becomes too complicated for us.
طبعا هنا السبين لديه خاصية غريبة يمكن تكون معروفة يعني من خلال الفيديوهات السابقة. انظر إلى سبين 0. ما هو سبين 0؟ الجسيم الذي يحمل سبين 0 طبعا هو جسيم هيجز. لهذا دعونا يعني نستثناه. أبدأ من جسيم من سبين النصف هي الفيرميونات. ورأينا في الفيديو السابق أن كيف لأن اللف المغزري كيف أن الفضاء ثنائي الأبعاد غير متناظر يفاعل اللف المغزري من أجل تحديد كتل الفيرميونات. طيب ماذا بعده؟ سبين 1 اللي هو فوتونات والدبليو زي. أولا نجد أن الدبليو زي أكبر كتلة من الفيرميونات، لهذا لها سبين 1، وسبين 1 أكبر من سبين هاف. ولكن الفوتون أصغر، لكن أصغر من ياته ناحية. نحن نتعامل بما يسمى بالكثافة الكتلية على وحدة الحجم. ربما الفوتون في أبعاده هو لديه كتلة أعلى من الفيرميون، أعلى من الإلكترون. الفوتون أبعاده صغيرة جدا، ربما في هذه الأبعاد الصغيرة لديه كتلة أعلى من الإلكترون. لهذا جاء له سبين 1. سبين 1 يعني اللف المغزر له أكبر من الإلكترون والبروتون وما إلى ذلك. لهذا نحن نتعامل مع شيء يسمى الكثافة الكتلية وليس الكثافة وليس الكتلة. الكثافة الكتلية اللي هو الكتلة على وحدة الحجم. طيب ماذا بعد ذلك؟ نجد أن سبين 2 هو الجرافيتون، وهو مسؤول من الكتلة، وهو سبين 2. ويقال أن الجرافيتون ليس لديه كتلة، لكن على مستوى يعني مثل الفوتون على مستوانا نحن لا نرى له كتلة، لكن على مستواه هو كتلته تكون عالية، وبالتالي الفضاء ثنائي الأبعاد فعل سبين عالي جدا له وأصبح سبين 2. طيب هذا يضعنا في تساؤل: هل هناك جسيمات سبين 1 هاف مثلا؟ هل هناك جسيمات سبين 3 سبين 4؟ الأمر يعتمد على الكتلة طبعا. لكن كما رأينا في الفيديو السابق لهذا مباشرة، الفيديو الذي يتحدث عن معادلة ديراك، وجدنا أنه الكتلة تتقسم إلى اثنين، تتقسم على الطاقة الحركية والإسبين، وبالتالي يمكن أن يحدد الفضاء ثنائي الأبعاد غير متناظر، يحدد الإسبين أقصى حتى إسبين 2، ويضيف الباقي الزيادة إلى الطاقة الحركية. ربما ذلك، أو ربما نجد جسيمات أعلى إسبين من الجرافيتون إسبين 2، الله أعلم.
Right now, and also not so important for particle physics applications. And so these are the two dimensions, and in this sense you can now see the complementarity, because this line here was the content of the quantum field theory lecture 2019 and 20. So we studied all these quantum aspects, but only for spin zero fields and particles. And in this semester we will cover spin 0, spin 1/2, and in particular spin 1, because spin 1 is extremely important and very rich in quantum field theory relationships. And it is of course important because in nature we know not so many fundamental spin 0 particles, but we know a lot of fundamental spin 1/2 and spin 1 particles. The spin 1 particles correspond to the fundamental interactions like electromagnetism or strong and weak force, and spin 1/2 corresponds to the electron and all other known matter fermions. Non-zero spin is crucially important, and here we will study mainly non-zero spin, and we come certainly up to the point of introducing interactions and studying them in detail, and we will also do a little bit of renormalization, but mostly we will be concerned with the specific special relationships related to spin 1/2 and spin 1. So this is here quantum field theory 22-23. And a main theme which runs through the lecture is the theme of gauge invariance. Because as we will see, spin 1 particles and fields are associated to gauge invariance, and that implies very specific relationships for interactions which can possibly occur in connection with spin 1 particles. And so we will study this, and we will go through a very important example theory, namely quantum electrodynamics, and we will study the physics of quantum electrodynamics in great detail, but from the point of view of generalization. So we will mainly use QED as an example of general quantum field theories with spin 1 fields, such that you can also see how it can work in more generality. Okay, so this is the complementarity, and that is our topic for this particular semester. Okay, let us come to our first real section of the lecture, background information. So we will not yet really start with quantum field theory, but I will collect 3 different kinds of aspects which you have already heard about in the past, but we will collect them here in a useful way because we will need them in the course of this semester. So we will repeat Lagrange and Hamiltonian formalism, which you know from your lecture on classical mechanics. We will repeat quantum mechanics for identical particles like bosons and fermions and the Fock space description of them, because that actually already is a quantum field theory, and I will make that explicit such that you can afterwards identify the relationship between our quantum field theories here and what we did in our quantum mechanics 2 lecture. And then we will briefly repeat also the theory of relativity, special relativity, and in particular I will collect some facts on the symmetry group which corresponds to special relativity, which is the Poincaré group. This group collects Lorentz transformations and translations and has special properties which we will need to understand what kind of relativistic quantum field theories there can be. But let's begin with our review of Lagrangian and the Hamiltonian formalism, and actually let us begin with the Hamiltonian. which is the opposite order, I guess, compared to what is usually done in classical mechanics. So let's begin with the Hamiltonian formalism, and let us motivate this formalism from a particular point of view. Let's go back many steps. Let us go back way back and ask, what is actually physics? What is physics at all? What is the science of physics all about? And okay, there can be many answers to this question, but we will try to answer it here in a technical and very straightforward, but still very general way. What is the purpose of physics and the purpose of a physical investigation? So first of all, in physics we have all of nature, and in principle our goal is to understand, first to observe phenomena in nature, and then to understand those phenomena, categorize them, find dynamical laws which govern those phenomena, and try to reduce the many diverse phenomena that we can observe to as few as possible fundamental concepts. Okay, but in technical terms, what we always try to do and have to do is, in physics, we need to first of all isolate a physical system. And then our physical system has to be observed. Phenomena have to be observed and categorized, classified, listed, and afterwards understood. And how does this understanding of a physical system proceed? In very general terms, we see that systems are physical entities which can be in certain states, as we call them. So there is the notion of a state of a system, and in general, a state is simply the maximum amount of information that you can have about the system at any given time. If you know the state, you know everything that you can possibly know about the system. You cannot know anything else beyond the state of a system. And so therefore one first very general task of physicists, if you are given a system, is to identify what are the possible states of this system. Once you know the possible states, you observe phenomena which are time-dependent phenomena, and then you want to understand the dynamics of the system. And dynamics means what are the possible time evolutions of the system. So in this way of thinking, physics is the science that evaluates and identifies the possible time evolutions of systems, and so if you can predict the time dependence of any physical system, you have understood as much as you can possibly understand in physical sciences. Therefore, this point of view highlights two particular concepts, namely the concept of a state of a system and the dynamics, in other words, the time evolution of a system. And so this is our task. And therefore, we can now, in very general terms, ask ourselves, what are the possible time evolutions in physical systems? What could they be? And therefore, let us write down some diagram and make some guesses. Okay, so here is a diagram. I draw it in 2 dimensions, and this diagram should be a phase-based diagram, as we call it. So this is a diagram where every point in the diagram corresponds to one particular state of a certain given system. And of course, you know from classical mechanics that there the phase space of a system consists of the P and Q variables, but that might not always be the case. So here we just mean any yet to be defined state with some dimensionalities. We don't know, but I draw it in 2 dimensions, and every point here that I draw corresponds to a different state the system can be in. Now I have drawn here 3 states, and the question is, what are the possible time evolutions? And so one first very fundamental observation in physics is that if you know your system well enough, if you know sufficiently many microscopic details, and if you know the state the system is in precisely enough, then you are always able to predict the future time evolution of your system. So the observation is that in physics is not random, but if you know sufficiently many initial conditions, you can predict the physical evolution of your system. And so let's draw this into this diagram. So let's draw the time evolution. Time evolution is typically continuous, but let's just simplify our lives by making time discrete. So let's say after 1 second, after 2 seconds, after 3 seconds, how does the state of the system evolve in terms of seconds, like stroboscopically? So for example, if we start with this state, then 1 second later the system might be in that state. And then this is a possible time evolution law. After 1 second the system changes its state from here to here. Another possible evolution law would be this. If at some time the system is here in this state, then 1 second later it might be there. So these are possible time evolutions. Now let's think about something else. Let us imagine a state here, some state, and the question is, can this be a possible time evolution law, such that if you start out with this state, 1 second later the system is in the same state, and then 1 second later again the system is in the same state, so the state reproduces itself all the time, so it's a stationary state which does not depend on time. Does this exist? Is this a possible evolution law? And the answer is yes, this is possible, and this is simply, for example, a particle at rest. Particle at rest doesn't change, and therefore its evolution law would look like this in a phase-space diagram. So this is possible. And this is also possible. So here, of course, it would have to go on somehow. So could it be possible, for example?
طبعا أنا نظريتي هي أيضا تقول هذا الكلام، أن في حالة الجسم، في حالة الحالة المستقرة، فإن معدلات تدفق الزمان حوله تكون واحدة، تكون ثابتة، وبالتالي يكون في حالة كمومية واحدة، أو نقول أنه مستقر تماما. لا، حتى لو كان يسير في بطاقة حركية معينة، لكن إذا سار بتسارع أو إذا سار في مجال جاذبي الأمر يختلف، لأنه المعدلات تدفق الزمان تختلف في المجال الجاذبي قربا أو بعدا من الكتلة. أما انتقال الجسيمات من حالة إلى حالة مع تطور الزمن، هذا أيضا تقول نظريتي، يعني في مثلا انتقال البروتون إلى نيوترون، وانتقال النيوترون إلى بروتون، هذا الأمر يدخل فيه التغير في معدلات تدفق الزمان والمكان أو الفرق بينهما كما رأينا في الفيديو السابق، ويدخل فيه عامل آخر وهو الفضاء ثنائي الأبعاد غير متناظر. فالفضاء ثنائي الأبعاد غير متناظر يحاول أن يحافظ على معدلات تدفق الزمان والمكان مستقرة، وبالتالي هو الذي يفعل هذه الآليات. يعني الانتر اكشنز التي سندرسها يعني لاحقا ما هي إلا ترتيب لطاقة كثيفة جدا في فضاء ضيق جدا جدا، وهذا الترتيب يفعله الفضاء ثنائي الأبعاد غير متناظر. يعني مثلا تفاعل بروتون وبروتون يخلق جسيمات كثيرة جدا. هذه الجسيمات قد تكون أكبر من البروتون، ولقد لاحظنا في الفيديو قبل السابق في المعادلة التي يحاول أن ينشئها من كتاب الحلقة 53 التي تخبرنا بشكل الكتل، تحدث عنها في فيديو 2 وفيديو 1. فهذه المعادلة هي عبارة عن دالة بين M small و M capital و R اللي هو نصف قطر التفاعل. كلما صغرت R كلما كبرت M small، وهذا يعني أن كلما كان التفاعل عميقا داخل البروتونات، يعني زدنا طاقة البروتونات المتصادمة أو الجسيمات، تعالوا نقول الجسيمات المتصادمة، فإذا زدنا طاقة الجسيمات المتصادمة فإنها بالتالي قللنا المسافة، قللنا R، وبالتالي الجسيمات المتكونة M small تكون كبيرة. لماذا؟ لأنه الجسيمات المتفاعلة اللي هو M capital بالإضافة إلى طاقتها تكون كبيرة. فكبر M capital وصغر R، طبعا R في المعادلة مرفوعة إلى القوة 2.5 أو 5/2، والكتلة M capital مرفوعة للقوة النص، وبالتالي نجد أن تأثير M small أو الجسيمات المطرودة من التفاعل تأثير يكون أكبر في بالنسبة لR. كلما صغرت R فإن سنضرب هذا القيمة ب 2.5 أو ب5/2، بالتالي M small تتأثر بقوة أكبر عند تصغير R. وثابت التناسب هو 10⁻⁻29 وهو رقم صغير، لكن نسبة لأنه الR صغيرة جدا ومرفوعة للقوة 5/2 فإنها يمكن أن تعادل هذا الرقم. وأيضا M capital يمكن أن تكون كبيرة في الأبعاد الصغيرة هذه، وبالتالي يمكن أن تخبرنا عن أيضا يمكن أن تعادل هذا الرقم. إذن نجد أن عند الأبعاد الصغيرة جدا فإن الفضاء ثنائي الأبعاد يلعب دورا كبيرا في هذا الأمر. وأيضا طبعا يلعب من أجل الحفاظ على مستويات تدفق المكان والزمان ويجعل الحالة مستقرة. لكن بالنسبة لكلام البروفيسور هنا الانتقال من الحالة الأولى للحالة الثانية كما في الانتراكشنز يتغير حالة الجسيم عند التطور الزمني. هذا يعني أنه موجود في مجال جاذبي أو موجود في مجال طاقة عالية كما طاقة التفاعل. طبعا يمكن تمثيلها بمجال جاذبي لأنه المجال الجاذبي والمجال الكهرومغناطيسي هو نفس الشيء عند يعني لهما نفس التأثير بالنسبة للفضاء، لأن الفضاء يراهما عبارة عن طاقة متكدسة. فالمهم هذا الكثافة العالية للطاقة تغير الفضاء حولها. كثافة عالية للطاقة متركزة في مكان واحد تغير الفضاء حولها أو السلايسز أوف سبيس أو تعالوا نقول مدارات في الفضاء. وبالتالي نجد أن معدل تدفقات الزمان والمكان تختلف، وبالتالي مع تطور الزمن فإن الجسم ينتقل من حالة واحدة إلى الحالة 2.
That we have something like this, 2 points, this goes into that after 1 second, and after the next second this goes into this, and then it goes back and forth all the time. Does something like this. Is this allowed? Yes, this is allowed, and this would, for example, correspond to an oscillation, a pendulum, which goes back and forth between 2 extremes, and these 2 might be the 2 extrema of the pendulum, here and here, and it goes back and forth all the time with a certain period in time. So this is also a possible evolution law. Now, how about this evolution law? So, for example, here, so that some evolution law like this. So here at this point we get 2 evolutions either here or there. That is of course not allowed, because that would mean that if we are in this state we cannot predict the future. It could be either this future or that future, and that is, as I said before, in fundamental systems not possible. In fundamental systems, if we know precisely enough what the initial state is, we can always predict uniquely and unambiguously the future behavior. So 2 such lines are not possible. And so we could write this down as a very, very basic postulate or an observation, which is, as far as we know, always true in physics. In fundamental systems, we can predict unambiguously the future. And of course, as I said many times, we need to specify the initial state with sufficiently much detail, and it might be a good question, what is sufficiently much detail? But if we have the details, then we are always able to predict the future. Now something else, would that be possible, for example, from here to here? So the system evolves uniquely, so here this goes uniquely here, that goes uniquely here, and that goes uniquely here, and then it oscillates in this way. Is this possible? Well, that is also not possible. So this looks like the system comes to a rest. You come from somewhere, for example, a particle is moving, then it slows down, and at some point it is at rest, and then the state doesn't change anymore. It stops evolving in time. That would be exactly the situation here. So that corresponds to something like friction. So that would be, for example, friction. And if we have such a situation, we can uniquely predict the future, but we cannot predict the past. The system has no unique past. If you are here, you could either have come from that point, or you could come from the same point here. Therefore, you cannot go into the past, you cannot extrapolate your system into the past. And this is indeed the case in macroscopic systems where you have friction and thermodynamics and so on, and equilibrium states. But it's again not possible to have this in fundamental systems with sufficiently enough detail.
طبعا بالنسبة لنظريته يمكن التنبؤ بالماضي. لماذا؟ لأنه نحن لا نرى المادة كسيستم قائم بذاته، وإنما نرى المادة بتفاعلها مع الفضاء، وبالتالي نستطيع أن نرى الفضاء، وبالتالي نستطيع أن نحسب الكيرفاتشر في الفضاء، وبالتالي نستطيع أن نعرف معدلات تدفق المكان والزمان، وأيضا سنعرف التغيرات التي تحصل في المادة. وبالتالي نظرية تستطيع التنبؤ في الماضي بالنسبة للفريكشن، وهذا واضح إذا ذهبت لكتابي الحلقة 50 الذي يتحدث عن WKB approximation أو semi classical approximation بعنوان adopting WKB approximation، وهو أننا قمت بمحاولة تجسيد التفاعل وخروج الجسيمات من التفاعل، حيث أن الجسيمات عندما تخرج من وسط التفاعل أو من فضاء كثيف إلى فضاء قليل فإن الكتل تتضخم والطاقة تقل حتى تصل مرحلة ويحصل بعد ذلك انتقال من التضخم إلى الاسكوليشنز. وأيضا إذا ذهبت الكتل من فضاء قليل الكثافة مثل فضاءنا نحن إلى فضاء كثيف مثل فضاء التفاعل، فإنها تضمحل، اللي هي قادمة من الاسكوليشنز إلى الاضمحلال. وبالتالي نظرية تستطيع التنبؤ بماضي التفاعلات أو ماضي حالات الجسيم في ظل التطور الزمان والمكان.
Okay, so that is a second observation, that this is actually impossible in fundamental systems. And so we can also write the observation is that in fundamental systems we can predict unambiguously the future and the past. And therefore in our phase-space diagram the possible laws of nature are such that every point in phase space has one arrow going in and one arrow going out. It has a unique future and it has a unique past. That is a restriction on the possible physical laws. So there are laws like this where the points and the arrows just go into infinity and so on. Okay, so this is possible. So it comes from somewhere in infinite and then it goes into some other direction. But every point has a unique past and unique future. You can have cycles like this, like in periodic systems. You can have stationary states, but you cannot have such a fork. Neither a fork into the future nor a fork into the past. So this is a fundamental observation. If we take this observation seriously and formulate it or use it as a postulate that all systems that we are now interested in behave like this, then we can ask, what is the general mathematical formalism by which we can describe all systems with this property? And for this question there is an answer in mathematics, and that is the so-called mathematical theory of dynamical systems. So there is a general formalism for that, which is called dynamical systems. So let me describe to you what the definition of such dynamical systems is. So in these systems, a state is defined by a certain set of variables, and let me call them here set I of t. And so in classical mechanics these could be the p and q variables, but let's call them in general zi of t. So this could be the position, momentum, or velocity, or something else that we don't know yet. And we say that the state uniquely specifies the time evolution. And what that actually means technically, so if we make time continuous again, then for continuous time, time evolution means the time derivative of those variables. So in this statement then means that if we have our zi's, we know them, we know the state perfectly well, then we also know zi dot. So the knowledge of z implies the knowledge of z dot. Then each state predicts unambiguously the time evolution, and so we can write this zi dot of t is equal to some function fi which takes as arguments all the z at the time t. This is the general definition of dynamical systems, and you see that it mathematically corresponds to a certain type of differential equations. This is a quite simple differential equation. It's a differential equation of first order in time, and the right hand side is some function of the set themselves. The right hand side doesn't depend explicitly on time, it only depends on zi of time. And so of course it can be still extremely complicated because these can be nonlinear functions, so it's not easy to solve those differential equations, but this is the general type of differential equation which implements our fundamental idea of physical systems, which are predictive into the future and predictive into the past. So this is essentially the most general mathematical formulation of such systems. So let's say this implements the above observation in a general way.
طيب كده الحلقة الأولى انتهت، وهذه الحلقة الثانية سنسجلها إن شاء الله في فيديو قائم بذاته. والحلقة الأولى ربما تكون واضحة وجلية، وربما تكون رأيتم الاتفاقات بيني وبين بالنسبة للobservable الذي هو عبارة عن z دوت هذا الobservable يخبرنا عن time evolution بالنسبة للobservable. يعني مثلا نريد أن نرى تفاعل الإلكترونات مع السمبليت يعني على السكرين، وبالتالي إذا أطلقنا يعني افرض في الدبل سليت أطلقنا الإلكترونات على هذا الحائل، فإننا نرى كثافة واحدة. طبعا هي صح تأخذ شكل الأمواج، لكنها في النهاية نرى كثافة واحدة هي مدرجة من ناحية البوزيشن، من ناحية المسافة، ولكن هذه الكثافة أو هذا النمط الباتر هو ثابت زمنيا، لكن ليس ثابت مكانيا. هذا أمر طبعا غريب، ليس ثابت مكانيا لكن ثابت زمنيا. وهذا ناتج من ماذا؟ هذا ناتج من أنه معدل تدفق الزمان بالنسبة للإلكترون في الدبل سليت هو 1، أو دعنا نقول أنه في الحالة النهائية هو 1، لكن معدل التدفق عند تفاعله مع السليت ليس 1، وبالتالي يختلف معدلات تدفق المكان والزمان في التفاعل. دائما في التفاعل تختلف معدلات تدفق المكان والزمان، دائما أبدا. أي تفاعل دون ذري، تفاعل جسيمات مع أي أوبجكت، فإن معدلات تدفق الزمان والمكان تختلف مع بعضها البعض. في جميع الحالات لا تختلف إلا في حالة الانتراكشنز أو في حالة الذهاب في مجال جاذبي أو مجال كهرومغناطيسي، فإن المعدلات تختلف. اختلاف المعدلات ينشأ عنها الكتلة مباشرة، إما بالزيادة أو بالنقصان كما رأينا في الفيديو السابق. فالدبل سليت تخبرنا عن هذا الاختلاف في معدل تدفق المكان والزمان، وبالتالي يعطينا constant time evolution but unstable position evolution. فنظرية أيضا تفسر بطريقة أعمق، كمان تفسر بطريقة أعمق من الميكانيكا اللي كان في موضوع الدبل سليت فينومينا. المهم، فهذه هي الحلقة الأولى. إن شاء الله ستتواصل الحلقات القادمة إن شاء الله بإذن الله تعالى.